The next geometry is octahedral electron domain geometry. In octahedral electron domain geometry, we have 6 electron domains. And as you can see, of those 6 domains, if they are all bonding, it'll be also octahedral molecular geometry, and we'll have domains where maybe one of them is non-bonding or 2 of them are non-bonding, and that'll change our molecular geometry to square pyramidal or square planar. So we're going to start off with the sulfur hexafluoride as our octahedral example. All right, with the sulfur hexafluoride, as we can see, we've got 6 electron domains around that central sulfur. Now that we have 6 electron domains, we've lost that difference in bond angle and everything's returned to a 90-degree bond angle. So axis to equator, we've got a 90-degree bond angle, and then around our equatorial position, we also have a 90-degree bond angle, right? Going back, and if I had that eye and I was looking down this fluorine, sulfur, fluorine bond, if I were looking down that, right, I would see fluorine, 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 right, at 90 degrees to each other around my equatorial position. So in this case, 6 electron domains, 1, 2, 3, 4, 5, and 6. All of them are bonding, so octahedral electron domain geometry and octahedral molecular geometry. 2 more molecular geometries in this group. This iodine pentafluoride and xenon tetrafluoride. So to do the Lewis structure for these, right, iodine has 7 valence electrons. I have 5 fluorines at 7 valence electrons each for 35 valence electrons. That's 42 valence electrons to assign. Iodine in the center, got fluorine, 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 fluorine. So right there, I just assigned 10 electrons to fluorine, to the surrounding fluorines. 32 electrons left to assign. I'm going to fill the octet of fluorine. So there's 6, there's 12, 18, 24, and 30. 2 electrons remaining. Those last 2 electrons will go on the central iodine. Yes, I've broken the octet rule for iodine, but that's fine because iodine has access to d orbitals. My electron domain geometry would be octahedral. My molecular geometry would be square pyramidal. I have 5 bonding domains, 1, 2, 3, 4, 5 bonding domains, and 1 non-bonding domain, putting me in that square pyramidal molecular geometry. Next, I've got xenon tetrafluoride. Xenon is a noble gas, so it's going to come with 8 valence electrons. I have 4 fluorines at 7 electrons each, so 7 times 4, right, would be 28 electrons there. So 36 electrons to assign, xenon in the middle, 4 fluorines, 1, 2, 3, 4, and that assigned 8 electrons. So that leaves me with 28 electrons. 28 electrons to assign. I'm going to fill the octet of fluorine. So there's 6, there's 12, there's 18, and 24 fills fluorine. 4 electrons remaining. Those last 2 electrons will be assigned to xenon. Fluorine cannot break the octet rule, right? Fluorine has 8 electrons, so the last 2 electrons would go on xenon. Electron domain, I have 1, 2, 3, 4, 5, 6 electron domains, which puts me in the octahedral electron domain arrangement. My molecular geometry, however, of those 6 electron domains, 1, 2, 3, 4 of those are bonding. So that would put me in the square planar molecular geometry. Right, and you might be wondering, okay, everything we've looked at up to this point was pretty easy because we just had one central atom to focus on, right? We just had the one central atom to count the electron domains and figure out, but how do we go from there? Well, what do we do next if we have a molecule with multiple atoms? Where do we pick and make the center? How do we set my electron domain geometry, my molecular geometry from there? And so we'll break down acetic acid here. I've got carbon 1, I've got carbon 2, and I've got my oxygen. So we're going to figure out the geometry around all three of those atoms. And we're going to do that by just doing the same steps that we did, except for just thinking about just focusing on carbon 1 first, and then carbon 2, and then the oxygen. So carbon 1 has 1, 2, 3, 4 electron domains. 4 electron domains, and all 4 of those electron domains, right? 1, 2, 3, 4, all 4 of those domains are bonding. So because of that, it is tetrahedral geometry, and I'd have 109.5 degree bond angles. Carbon 2. Okay, around carbon 2, I have 1, 2, 3 electron domains, right? This carbon-oxygen double bond counts as one domain, even though there's 2 bonds there. So 3 electron domains, they're all bonding, right? This would be trigonal, planar. And my bond angles would be about 120 degrees apart. So even though these are drawn as 90 degrees and these are drawn as 180 degrees, that is not the case. This molecule will actually be tetrahedral geometry here with 109.5 degree bond angles, trigonal planar here with about 120 degree bond angles. And now for the last one, oxygen. Oxygen has 1, 2, 3, 4 electron domains. Of those 4 electron domains, right, my electron domain geometry would be tetrahedral based on those 4. Of those electron domains, 2 are non-bonding and 2 are bonding. And that would put us in the bent molecular geometry with, again, about 104.5 degree bond angle. So that's how you would figure out the geometry in a larger molecule, right? You do the same steps. Identify an atom that you're curious about the geometry of, and then determine how many electron domains are around that central atom. And then after you've done that, of those electron domains, how many are bonding, how many are non-bonding, what molecular geometry does that place you in? Next class, we're going to take a look at hybridization, hybrid orbitals. So what orbitals are we using to form these carbon-hydrogen bonds or this carbon-oxygen bond, or what orbitals is oxygen using to form the oxygen-hydrogen bond in acetic acid?